The speed at which we do things often affects their outcome. If we have a detailed task, it's often better to take our time and to do them slowly so that we don't make any mistakes. Whereas sometimes it can be better to do a task fast. This video shows two cars. If the cars go fast enough, they can momentarily defy gravity and complete the loop. Compared to atomic timescale, this is still quite slow. What happens when we make a system respond on a timescale much faster? How fast can we drive a system, and what new effects can we see in these systems? My name is Simon Wall, and I lead the Ultrafast Optical Dynamics of Solids group at ICFO. Our aim is to use short flashes of laser light to change the internal structure of materials. We do this to try and understand how the materials work by monitoring how this energy is transformed throughout the material. In a solid, atoms are typically vibrating backwards and forwards very rapidly with a timescale of about 100 femtoseconds. Now 1 femtosecond is 1 billionth of a second. So to excite these systems, we need to use short pulses of laser light, which are much shorter than this timescale. These light pulses affect the electrons within the material, which changes the glue which is causing these atoms to vibrate. After the flashes, electrons are excited, and this affects how atoms move. In this time, the material properties are changed and new states of matter can emerge, which we can measure through measuring the changes in reflectivity or the conductivity. And this allows us to observe these new states of matter in the time domain. One place where we apply this is to study phase change materials. Phase change materials are already widely available in your rewritable DVDs. These are materials which have two states, one which is highly reflective and one which is very transparent. And this is used to encode the ones and the zeros of your data. Now, when the material is heated, you can drive it from one state to the other. But during the heating process, the electronic and structural properties change at the same time. And it's not clear whether it's the change in the structure or change in the electronic properties which is really driving the change in the optical properties of the material. Now, when we do this in the time domain, we can actually answer this question because we can observe what happens to the reflectivity or the transmission of the samples before the atoms have had time to move. And this allows us to determine the contributions of the electronic effects to the structural effects. These results have several important implications. It tells us that we can drive very large changes in the optical properties on very fast timescales using short laser pulses. So these could be used for optical switches in communications, allowing us to operate at very high speeds. It also tells us what the fundamental speed limit is for changing the properties of these materials, and ultimately how fast we'll be able to use them in the future. In the future, we want to apply this technique to more materials, so to look at how the laser can influence the magnetization of a sample, or what happens when we look at even more complex phenomena like superconductivity. In addition, we'd also like to see, can we drive a material into states that are never normally occurring, and what are the properties of these states, and can they be useful in future applications? These are projects that we would like to study over the next few years. I was always interested in space since I was a child, and that's what got me interested in studying physics. But it wasn't until I went to university when I realized that actually materials are equally as fascinating and as complex as maybe even the entire universe. What's more is that you can actually study materials much more easily in the lab and find out about these interesting phenomena.